Hello, my name is Thomas. I'm a researcher. I've been working with alternating hemiplegia of childhood and ATP1A3 related diseases for now almost 5 years. I originally joined Kai Lykke Hartmann's research group in Aarhus at Aarhus University, where we've been working on characterizing a mouse model for ATP1A3 related diseases. We've recently published a paper on this, and I've now moved on to Northwestern University at the laboratory of Dr. Alfred George and Jennifer Kearney. They have a huge interest in genetic modifiers in the laboratory, and we are now looking into investigating new ways of attacking these diseases by identifying proteins or other components of the disease that might be addressed pharmacologically. I have been part of this AHC community for almost the entire time now, and I've attended all the annual meetings since back in Rome, and I've learned a tremendous deal by talking to physicians and the families, and it's been an extreme privilege and a great journey for me to be part of this process, and I think that it's something that we all benefit profusely from. Yeah. So where are we headed? I think ATP1A3 it's a protein that has been really difficult, I think, for us researchers to address, in the sense that it has such a central function in the central nervous system. That there are a few ways of actually trying to right now to bypass and to alleviate the symptoms that the patient have by stabilizing the protein itself. And this is why I think that we are now looking into other ways of maybe stabilizing the patients. I think what has come out of many of these meetings is that even within the same mutation in the protein, the patients show very different disease causes, and I think that suggests that this is not the only protein that actually affects the disease cause. My reason for moving to the United States recently was actually to look into this in more detail and to actually hopefully in a not so distant future to identify what we call disease modifiers, essentially other proteins in the patients that might actually help stabilize symptoms. It's a quite well-known fact that up to 50% of patients suffer from epilepsy, but it's not really known why the other 50% do not show the same symptoms. It's quite evident that the severity of epilepsy is quite it correlates with the severity and degradation of the patients. So ultimately, we would like to, let's say, be able to, for instance, stabilize epilepsy by looking into other genes that somehow are modifying the outcome. And by identifying these genes, we would actually identify new treatment targets. So in the end, we hope to be able to, at least in some way, bypass the current restrictions we have in focusing only on ATP1A3 as let's say, disease cause. So my goal for the next couple of years, hopefully, is to be able to patch together a handful or more candidates that we can begin looking into, and I think this is the first step to maybe beginning to understand more of how individual patients actually are we able to treat them and essentially also to maybe go forward on what we call personalized medicine. Because I think it's at the point I think we were extremely lucky to have several animal models that adhere so closely to the disease, but we I think far still from taking the step from translating what we see in the animals to actual patients. But we hope to minimize this gap by continuing to use these mouse models. And even more mouse models I know are underway, so I think we'll be able to hopefully even better understand the diversity that we see in the patients by simply looking at these mouse models and using them as the extremely invaluable tool they are. I think my experience in the field is relatively limited at the time, but the laboratory I am in have been doing this for the last many years now, and they have a lot of experience in what I consider, at least in some ways, to be a very closely related disease called Dravet syndrome. And they have recently published several papers identifying new treatment targets for this disease, and I think that it's very likely that we will be able to follow the same path and actually be able to at least cut some corners by using the extreme amount of experience that is already in the lab. So I think for us, I think it's a matter of going forward and pressing through, and I hope within, let's say, maybe a couple of years, we will be able to at least delineate some new targets that we will be able to look into. And we have collaboration with several companies that will be able to help us address these targets in one way or another. So I think that we already now looking into different pharmacological approaches for the mouse that I'm working with, and I think this is a natural continuation that we will actually begin to sort of address this from several angles, that we will not only, let's say, use the more traditional approach of trying to treat what we see, but we will actually trying to maybe go one step further and actually try to identify why the symptoms arrive in the first. And I think this is the right way to do it, and I think it's in the end it's going to be what actually helps us getting more information about the disease, because right now, even though we've been focusing on this for now a number of years and we've identified this protein as being the target, I think we still have so much ground to cover in terms of why different mutations don't behave the same way, why different patients degrade over time, whereas other patients do not, even within the same family, and so on. So I think that this is just sort of opening a new chapter in this research book we have now started writing, and I think it's I think it might be a extremely important step to take, because I think we need to look outside the box in terms of attacking this disease.